Good morning, lads and ladies. Welcome back to Calculus. Today is our last day of regular lecture. Congratulations. Here we are. The name of the game today is to wrap up what we've been doing in polar coordinates. So we've come to a place now where we're reasonably comfortable graphing functions in polar coordinates, where we can calculate the slope of a tangent in polar coordinates. The natural thing to do from here is to kind of progress along that system of calculus operations to finding areas bounded by polar curves and even discuss, a little bit arc length in polar coordinates or for polar curves. So that's what we're going to do today. Let me go ahead and fire up the doc here. And we can get started. All right. So this, as always, is MAC2312, section 004, which is a Calc 2 class. And this is our last time drawing this title card on the 20th of April, 2022. Today, we're going to talk about area and arc length. Polar coordinates. And this is section 10.4. So it's the very last section we're going to cover in this class. This material is not going to show up on exam 3. This will show up only on the final. There is a homework set that I've published related to this section, and it is for some of the tangent stuff and arc length, area, and polar coordinates. That homework is set to be due on the day of the final, so you don't need to rush it, but we do need to discuss it. So let's do that. Begin by saying, sorry. Hey, Alex, I'm actually teaching right now. Can I call you back in a minute? Great. So recall that most polar curves come from functions of the form r equals some function of theta. I'll just write r of theta, right? Like r equals 1 plus sine theta. We were looking at those the other day. That's a cardioid. R equals 2 cos theta. That's a circle. R equals cos of 2 theta. That's a pedal graph. And these graphs, kind of in the most general and abstract sense, look something like this, right? Here's just a curve in polar coordinates, we'll say. What I want to do is find the area bounded by this polar curve between the two angles alpha and beta here. This class does not actually, this is taught out of Stewart, so we don't use an OpenStax book for this class, but I can send you a PDF. Yeah, I can do that. Give me just one moment, maybe I'll paste it in the chat or something. So the first idea I want to get through regarding these areas that we're going to be calculating is that they're not areas under the curve, right? It's in the polar setting, as the output gets smaller, rather than going down, right? Because when you go down, y gets smaller, and that's what we're used to thinking of. So we're thinking of areas under curves. In polar coordinates, as the output, which is r, as that output gets smaller, you're coming in towards the pole. You're coming in towards the origin here. So rather than finding an area under a curve, we're kind of finding an area inside of a curve. And it's a slightly different thing to think about geometrically. But this is what we want. We want to be able to calculate this area where the curve here is some function of theta. So we're going to find the area bounded by the polar curve r equals r of theta as theta goes from alpha to beta. And that will be some sort of wedge like this in general. A prerequisite for this, a little thing we need to know ahead of time, is how to find the area of a sector of a circle. So what do we mean by a sector? Well, if you take a circle, but only consider a portion of it, like this, where this angle here is theta and this radius here is r, right? Of course, you can imagine there's a whole circle here. But if I just want to find the area of this sector, how would I do that? The reason we need this is because I'm going to think of the area bounded by our polar curve as being chopped up into a bunch of little sectors, right? Instead of having little Riemann rectangles, we're going to have like little Riemann sectors. The way you get here is by thinking, well, the area of a whole circle is pi times the radius squared. The area of half of a circle should be 1/2 pi times the radius squared. And the area of a quarter of a circle should be 1/4 times pi times the radius squared. So in general, what we get here is 1/2 times theta times r squared. Right? This is the only formula that works. If you plug in 2 pi for theta, then the 2 and the 1/2 cancel and you get pi r squared. If you plug in 0 for theta, of course you get 0. If you plug in, pi over 4 for theta, then you'll get 1/8 of pi r squared, or 1/8 of the area of the circle. So we're going to use this and chop this area up here into a bunch of little things, a bunch of little slivers, and each one of those slivers we're going to approximate as a sector of a circle. All right. So this is kind of where we're going to go. I'm going to redraw this picture on the next page, only larger, and I'll show you how we get there. So with this prerequisite out of the way, let me lay out the setup. So to find the area bounded by the curve r equals r of theta, where alpha is less than or equal to theta is less than or equal to beta, we will partition the theta interval alpha to beta into n equal length subintervals, each with length, we'll call it delta theta. So very similar to what we do with a regular Riemann sum, only here the the interval alpha to beta is as an interval of angles, we're going to chop this up into n equal length subintervals, so like n little tiny angles in here. And because they need to be of equal length, that length is going to be beta minus alpha over n. What we'll do from there is use those little delta thetas to chop up my region. So here's the angle alpha. Here's the angle beta. Yeah, I'm just redrawing that picture we had a minute ago, only larger. This is the curve r equals r of theta. And the area I'm after is all of this. So sort of the area inside the polar curve. Now the partition that we have here, the delta theta partition, is going to split the angle in here into n little angles, which I will attempt to draw in. I'll ask you to be patient with me because these are a little tricky. I'll only draw a few of them. Something like this, right? And each one of these little angles in here is delta theta. And instead of a little Riemann rectangle, what I'm going to have is a little Riemann sector. So I'm going to approximate the area bounded by the curve there as the area of this little Riemann sector. I'll shade in dark pencil. And when we do this, what we're doing is the exact same thing we do with a regular Riemann sum. I'm assuming that on a small enough interval of inputs, the function is constant, right? When we use a rectangle to approximate the area under a curve on a little delta x interval, what we're doing is we're saying the top of that curve there, maybe it's not really flat, but if the rectangle is small enough, it's very, very close to being flat. So on each delta theta interval, we approximate the area bounded by r equals r of theta as the area of the sector of the circle, or of a circle, whose radius is this, right? So I would call this like R. This is R of alpha. This is R of, call it theta 1. This is R of theta 2. And in general here, I'll call this R of theta I, right? So my interval from alpha to beta has been chopped up into n equal sublength intervals, the endpoints of which I call theta 0, theta 1, theta 2, out to theta I. Right, that's the idea. And we continue on and on like this. This last one would be R of beta. So the black curve isn't exactly a circular sector, right? It's not exactly a circular arc, but as long as delta theta is small enough, this little error space here, the little bit that's missing, is very, very small. And as n goes to infinity, I use infinitely many of these little sectors, that error is going to go to 0. So we will get an exact area. This sector has area 1/2 times the angle inside the sector, which is delta theta, times the radius of the sector. The radius of the sector is R of theta I, and then we square it, right? This is using that formula for this area of a sector, 1/2 theta R squared. Well, the inner angle here is delta theta, so that's what I plug in for my angle. And the radius of this sector is the output from the function R, evaluated at that angle theta I. Hence, the total area bounded by the curve is approximately the sum of all the little areas. So write capital sigma I from 1 to n, where I is like, this would be I equals 1, this would be I equals 2, this would be I equals 3, and so on, of the little areas, which is 1/2 delta theta times R of theta I squared. And if I want to, I can rewrite that. This might seem a little bit silly, but as sum from 1 to n, 1/2 R of theta I squared times delta theta to make it look just a little bit more like a Riemann sum. And as n goes to infinity, the approximation becomes exact as the sum, the Riemann sum, becomes an integral. And this gives us the formula for the area bounded by a polar curve, which is the integral from alpha to beta of 1/2 R of theta, your function, squared d theta. This is the piece you need to remember. Questions on the work we do leading up to this integral formula? Okay, let's try some calculations. So make sure you save this formula somewhere. This is the formula for the area bounded by a polar curve. Let's find the area inside the polar curve r equals 1 plus sine of theta So they haven't specified theta values for us. We need to figure those out. They haven't shown us what the curve looks like. We should take a look at that. And then we'll need to set up the integral. By now, you should be able to tell me what this curve is. So what is the shape of this curve, 1 plus sine theta? Anybody know? Yeah, there we go. It's a cardioid. The drawing here doesn't have to be perfect. But if you remember the basics, just like graphing parabolas and stuff, if you remember the basics, then you can plug in just a few values and have a really nice concrete picture. So when theta is 0, when we're over here along the polar axis, r is 1 plus sine theta. That's 1 plus sine of 0 is 1 plus 0 is 1. So I've got a cardioid here. I know I've got, if I mark this as 1 on the polar axis, I know I go through here. When theta is pi over 2, r is 1 plus the sine of pi over 2. Sine of pi over 2 is 1, so that's 1 plus 1. So that means we're going out here to this point, whose polar coordinates would be 2 comma pi over 2. The polar coordinates here are 1 comma 0. When theta is pi, sine of theta is 0 again. So we've got the polar point here, which is 1 comma pi. So this is a cardioid that's kind of flipped upside down, right? And of course, when theta is 3 pi over 2, we're at the origin. So the curve here is something like this, and then the cusp in here. There it is. So I'm looking for the area inside this curve, all of it. This area, together with all of this area, together with all of this area. I'm looking for all the area inside this cardioid. There's a few nice ways you can exploit symmetry here. We could set up the integral. So let me first just write down the kind of obvious thing. We know our formula for area. I'll start by just writing that down. It's the integral from alpha to beta of 1/2 r of theta squared d theta. R of theta here is 1 plus sine theta. And we could do this as the integral from 0 to 2 pi. Right? As we rotate all the way around, theta equals 0, pi over 2, pi, 3 pi over 2, 2 pi. So we could do the integral from 0 to 2 pi of 1/2 times 1 plus sine theta all squared d theta. But I can also exploit symmetry very nicely, and we should, wherever given the opportunity. And there's a lot of opportunity in polar coordinates. We should use the symmetry. So the dark shaded area here, if I multiply that by 2, I will get the total area. Agreed? So I could, instead of thinking of this as the integral from 0 to 2 pi, think of it as the integral from negative pi over 2 to pi over 2, and then just double it. So this is the same as 2 times the integral from negative pi over 2 to positive pi over 2 of 1/2 1 plus sine of theta all squared d theta. You won't get the wrong answer if you don't do this, but there will be a lot of problems where the integral is easier if you do this. And generally, exploiting symmetry is a good thing. It's a skill you want to develop. Do we see why these new bounds are what they are, negative pi over 2 and pi over 2? You could also do it the other way. You could integrate from pi over 2 to 3 pi over 2 and calculate the area on the left and then double that. That would work also. But this is nice in that it's symmetric with the bounds as well. The 2 out front here, when I pop out this 1/2, will cancel. So let me take this over here. I'll have the integral from negative pi over 2 to positive pi over 2. The 2 and the 1/2 cancel, so this will just be 1 plus sine of theta all squared d theta. And then to do that integral, you have no choice. You have to multiply things out. So that's the integral from negative pi over 2 to positive pi over 2 of 1 plus 2 sine theta plus sine squared theta d theta. And then the sine squared theta, right? We know how to integrate 1. We know how to integrate 2 sine of theta. How do you integrate the sine squared of theta? Who remembers that from section 7.2? Very good. Yeah, this is a half angle identity. So here we need to use the identity sine squared equals 1/2 1 minus cos 2 theta. So it's going to give me integral from negative pi over 2 to positive pi over 2 of, all right, 1 plus 2 sine theta plus 1/2 times 1 minus cosine of 2 theta d theta. Then I'll distribute this 1/2 and combine like terms. Should give me integral from negative pi over 2 to positive pi over 2 of, I've got a 1 here, and when I distribute this 1/2, I'll have a plus 1/2. So this is going to be 1/2 minus 1/2 cos 2 theta. And I'll take this 1 together with this 1/2 to get 3/2. Then I'll still have my plus 2 sine theta. And then I'll have minus 1/2 cos 2 theta. So take a second, make sure you see where everything's coming from. Any questions so far? So I'm choosing, rather than to integrate from 0 to 2 pi, integrating from 0 to 2 pi would be going like around like this. So starting at 0, integrating all the way around to 2 pi. What I'm deciding to do instead is to just calculate the area of the piece on the right. Now, if I were to go from 0 to pi over 2, that would miss this bottom piece. So instead of thinking of this down here as being like 3 pi over 2 to 2 pi, I'm thinking of it as being negative pi over 2 up to 0, and then from 0 up to pi over 2. So this region on the right, I can think of as being from negative pi over 2 to positive pi over 2. And that will give me half of the area I need. Does that make sense? Cool. All right. So from here, life is good. We can now see what our antiderivative is, because each one of these is a pretty simple function. If I integrate 3/2 d theta, I'm going to get 3/2 theta. Remember, this isn't an x here, it's a theta because we're doing the integral d theta. If I integrate sine 2 sine theta, that's going to be negative 2 cos theta, because the derivative of cos theta is negative sine. And if I integrate 1/2 cos 2 theta, I would get this, just the cos 2 theta would be like sine 2 theta over 2, or 1/2 sine 2 theta. Because there's already a 1/2 here, this is going to be, the minus stays here, 1/4 sine of 2 theta. It's a micro u sub. And we're evaluating this from negative pi over 2 up to positive pi over 2. Okay, good news here. The cosine of pi over 2 is 0. Right? You plug in pi over 2 to cosine, you get 0. The cosine of negative pi over 2 is 0. So this piece is 0 at both bounds. So is this piece. It's not the sine of theta, remember, it's the sine of 2 theta. So maybe I'll write it out. I don't want to cause unnecessary confusion. We've got the space. So at the upper bound, I'll have 3/2 times pi over 2 minus 2 times the cosine of pi over 2 minus 1/4 times the sine of 2 times pi over 2, which is pi. And then at the lower bound, I'll have 3/2 times negative pi over 2 minus 2 cosine of negative pi over 2 minus 1/4 times the sine of 2 times negative pi over 2, which is minus 1/4 times the sine of negative pi. And we could have skipped writing most of this, but I just don't want to overwhelm. The reason we could have skipped writing most of this is because this is 0. Cosine of pi over 2 is 0. This is 0. Sine of pi, definitely 0. This is 0. Cosine of negative pi over 2. Cosine is an even function. Sine of negative pi, that's also 0. So the majority of the terms here are 0. In fact, the only contribution comes from the 3/2 theta.
That won't always be the case, but it's not rare in these problems, especially if you use the symmetry, right? That's one of the reasons we like using the symmetry so much. So what isn't 0? I've got 3 pi over 4 here, 3 pi over 2 times 2, minus 3 times negative pi over 4. So it's minus negative 3 pi over 4. And of course, minus minus makes plus, so that's 6 pi over 4 or 3 pi over 2. And that, my friends, is the answer. This is a great problem. This is about as hard as you should expect the problems related to this to be on the exam. Again, this won't be on exam 3, this will only be on the final. But this is about that level of difficulty. Questions on this guy? Okay, let's try one more before we talk about Arclengths. Let's find the area of one petal of the curve R equals about sine of 2 theta. Or you could say loop here. You'll see the word loop sometimes. Again, in order to know what we're doing and to have any idea what sort of symmetries we might use, we need to draw the curve. So I asked you last time, can you find the relationship between like sine n theta and the number of petals in the graph? I'll go ahead and reveal the answer to that question in the form of a recall. R equals sine n theta or cos n theta are petal graphs with either 2n petals or n petals. Did anybody discover this rule? Nobody did this, we should do it together. So R equals sine 2 theta. R equals sine 4 theta. Okay. Sine 2 theta has 4 petals. Sine 3 theta has 3. Sine 4 theta has 8 petals. How many petals will sine of 5 theta have? Very good. Sine 5 theta will have 5 petals. And what about sine of 6 theta? Good. So what's the relationship? If n is odd, then you'll have n petals. And if n is even, you'll have 2n petals. So the sine of 2 theta is going to be a petal graph with 4 petals. The cosine petal graphs always have their first petal like centered on the polar axis here. The sine petal graphs are a little bit different. They're rotated, just like you notice with the sine and cosine cardioids and all the other stuff, right? The sine petal graphs are their first petal oriented somewhere in quadrant 1. So this guy would look like this. And then come over here. And then he would come over here. And then he would come up here. Back with the start. So the area of one petal is this area. And we need to figure out our bounds, right? We need to figure out the theta values that correspond to this petal starting and this petal stopping. So when I first start drawing here, theta is 0. I don't know what this theta value is, and I don't know what the theta value is when I come back in. So let me sketch the rectangular graph really quickly, and that will help us. Sine 2 theta is periodic with period pi. So we have to go through a full cycle for the sine function as theta goes from 0 to pi. The amplitude is 1. So my regular graph of this function as a wave is going to look like that. I do want to make a little note here. The first petal does come from this first arc, but the area of this arc is not the same as the area of this petal. Warning, I'll shade this red. So the area in rectangular coordinates, which I've shaded red there, is not equal to the shaded area on the purple graph. It's true that this part, these theta values, the theta values here from 0 to pi over 2, are the theta values that sweep out this portion of the polar curve. But it's not true that the areas are the same. Right? When you transform the graph from rectangular into polar, it stretches things out some places and it compresses things in other places. It is not an area preserving transformation. But this will help me figure out my bounds. So if one full cycle here is 0 to pi, and I go out and then back in, because r goes from 0 to 1 and back to 0, then this guy must be pi over 2. This max here is occurring at pi over 4, so this would be the polar point 1 comma pi over 4. And then the first time we go back into the origin, that's the polar point 0 comma pi over 2. So the integral I need for the pencil shaded area over there is equal to the integral from 0 to pi over 2 of 1/2 times r of theta squared, which is sine of 2 theta squared. d theta. Oh, I should finish the sentence I wrote here. So the area in rectangular coordinates is not equal to the area in polar coordinates. Reasonable thing to think, but it's not true. Okay. This integral, I'm integrating an even power of sine. It just happens to be a sine of 2 theta. So the procedure is more or less the same as what we did in one part of the previous problem. I'll pop out the 1/2, integral 0 to pi over 2. And this is just sine squared of 2 theta. 2 theta. And then we use that half angle identity again. The identity I'll write it as sine squared of x is 1/2 times 1 minus cosine of 2x. If you plug in 2 theta for x here, and we had to do this a lot back in 7.2, I'm sure you remember, you get sine squared of 2 theta equals 1/2 times 1 minus cosine of 2 times 2 theta, which is 4 theta. So I can replace my sine squared of 2 theta. I've still got my 1/2, still integral 0 to pi over 2. Sine squared of 2 theta is 1/2, 1 minus cosine of 4 theta d theta. Pop out the 1/2. You get a 1/4 out front. Integral 0 to pi over 2, 1 minus cosine of 4 theta d theta. And then your antiderivative is not hard to find. So it's 1/4 theta minus sine 4 theta over 4, evaluated from 0 up to pi over 2. All we got to do is plug in the bounds. And like last time, right, if I plug in 0 for theta here, sine of 4 times 0 is the sine of 0, which is 0. If I plug in pi over 2 for theta here, 4 times pi over 2 is 2 pi. Sine of 2 pi is also 0. So again, the only contribution comes from the theta piece. I'll have 1/4. I'll write it as pi over 2 minus 0. And then I subtract what I get when I plug in 0, which is 0 minus 0. And that's pi over 8. So that's the job done. Questions on this guy? Bye, baby. Okay. then that's all I'm going to do as far as examples for areas. There are some problems in your homework that are slightly more complicated, but nothing too bad, right? So you can get there. Just remember, exploit symmetry where you can and draw the graph, right? Practice drawing the graphs. Don't feel bad if you use Desmos to help you, but make sure you're learning as you go, right? Like this rule, really good to commit to memory. It's not hard to remember. If you're unsure, you can always sketch the rectangular graph and then transfer it over like we were doing before. Are you ready? Here's the very last thing you need to learn in Calc 2. Very last thing. Arc length in polar coordinates. When we talked about tangents in polar coordinates, the thing that really allowed us to get the job done that we can parameterize the polar curve r equals r of theta as x equals r of theta times cos theta and y equals r of theta times sine of theta. And this led to dx d theta being dr d theta times cos theta minus r of theta times sine theta, and dy d theta being dr d theta sine theta plus r of theta cos theta. Just taking the derivative of each of these with respect to theta. We had to use the product rule. We did this all last time. We know the arc length for a parametric curve is the integral of the square root of dx dt squared plus dy dt squared dt. And this is done from, A to B. Well, these are parametrized, but with the parameter theta. Oh, nice. So the only difference is we're going to use the variable theta here instead of the variable t. Therefore, the length of a polar curve. God damn, I'm sorry, guys. I don't know what this is calling me. Good Lord. Okay. Therefore, the length of a polar curve from theta equals alpha to theta equals beta is, well, it's going to be the integral of this squared plus this squared done from alpha to beta. Now we're going to simplify this quite a bit, and I'm not going to show all the steps because it is a little messy. This is the integral from alpha to beta. I'll plug it in here. That's dr d theta cos theta plus r of theta, sorry, minus r of theta sine theta squared plus dr d theta sine theta plus r of theta cos theta all squared, all under the square root with the d theta at the end. Now let's go ahead and imagine you FOIL both of these out. From this first guy, you'd have dr d theta squared times cos squared theta. From this guy, you'd have dr d theta squared times sine squared theta. When you put those together, you're going to have dr d theta squared times cos squared theta plus sine squared theta. So cos squared plus sine squared, that's 1. So there's going to be a dr d theta squared under there. Your last term here is going to be r squared sine squared theta. Your last term here is going to be r squared cos squared theta. Again, put those together, you'll have r squared times sine squared plus cos squared, which is 1. And then the cross terms, you would have minus 2 dr d theta cos theta r of theta times sine theta. And here you'd have plus 2 dr d theta sine theta r theta cos theta. Those will cancel. So what we get, I'll say, and after simplifying the radicand, this becomes L equals the integral from alpha to beta. I'm gonna check my mental algebra there for 1 second, make sure I'm giving you the right results. Without writing it out, it is possible to make little mistakes. We're in 10-4. Yep, dr d theta squared and r squared, just those. So I like to write it this because it comes from the lead term. And so everything else cancels. So here it is, the very last formula in Calc 2. Arc length of a polar curve. So you can think of them as parametric curves and go through the whole rigmarole there, but it's much, much faster when you're working with a polar curve to go ahead and stay in polar land, right, and do the integral d theta rather than trying to convert it into the parametric thing and multiply all that bullshit up. So before I let you go, I want to do at least one calculation using this, and then we can, if there's time, take a second to talk about anything you guys would like to talk about. Yeah, that's a fun one. This is actually a very tricky integral, but I'll go ahead and sort this out for you. So make sure you get this down nice and neat in your notes. You don't have to have the derivation if you don't want it, but I do think it helps understand. Let's find the length of that cardioid. Find the length of the full cardioid. R of theta equals 1 plus sine theta. It's the same curve that we drew before. The bootyoid, right? It's the cardioid that looks like a booty. It's 1, and 2, 1, and the origin. This guy. You can't unsee it, can you? All right. I'm going to execute this the same way we did the area problem for this. I'm going to try and exploit some symmetry. So yes, I could do the integral. What's our formula? The length is the integral from alpha to beta of the square root dr d theta squared plus r of theta squared d theta. So I could, I need to calculate our dr d theta. That's the regular derivative of r of theta, right? R is a function of theta, so dr d theta is just what you get when we take the normal derivative here. 1 differentiates to 0, sine differentiates to cosine. So we get L equals. We can integrate from 0, right? Here's theta equals 0, all the way around to 2 pi. Of the square root of dr d theta squared, which is cos theta squared, plus r of theta squared, which is 1 plus sine of theta squared. Okay. And you know the squares and the square root, they don't cancel because of the addition going on inside here. So we have no choice but to follow things out. Before we do that though, observe in the same fashion as last time, that I can do this as 2 times the integral from negative pi over 2 to positive pi over 2. I'm going to take the length of the right half and double it. And calculate this, which I can think of as the negative pi over 2 to pi over 2 and double it. And there's a good reason on this problem for doing that. I'll point it out when we get to it. So cosine theta squared is cos squared theta. 1 plus sine of theta all squared is 1 plus 2 sine of theta plus sine squared of theta. Okay. The cos squared plus sine squared here adds up to 1. So I've got between the two blue pieces 1 plus 2 sine theta. So altogether that's 2 times the integral from negative pi over 2 to positive pi over 2 square root of 2 plus 2 sine theta. Okay. This is a tricky integral. Can anybody suggest how to evaluate this integral? Think back to all that work you did in the early part of this course. Excellent. I'll multiply by the conjugate. So the squared is what's giving me a headache. I would like to produce a perfect square under that square root. And the easiest way to do that is inside the square root here, I'm going to multiply well, here, I'll do it like this. This is 2 plus 2 sine theta. I'm going to multiply by the conjugate of this expression, top and bottom. So that'll be the square root of 2 minus 2 sine theta. And if I'm going to multiply by that upstairs, I have to multiply by that downstairs. This is a sneaky trick, and this is harder than something I would put on a test, right? Because the integration step here requires some real creativity. But now the numerators you can combine into a single radical. Upstairs here you'll have 2 plus 2 sine theta times 2 minus 2 sine theta, all under one square root, because squares do play nice with multiplication. And downstairs, you'll have the square root of 2 minus 2 sine theta, theta. This is the move, because when you multiply by the conjugate, that numerator is going to become very nice. 2 times 2 is 4, plus 4 sine theta minus 4 sine theta, 0. And then the last are minus 4 sine squared theta. Downstairs, we still have the square root of 2 minus 2. This gives me 2 times the integral from negative pi over 2 to positive pi over 2. 4 minus 4 sine squared theta is the same as, I'm going to do this on the side. This is looking a lot like some trig sub stuff we did. That's 4 times 1 minus sine squared theta, which is 4 cos squared theta. So that numerator is the square root of 4 cos squared theta. And the denominator is still the square root of 2 minus 2 sine theta. Here's the sneaky bit. The reason the symmetry here is so important when I'm integrating from negative pi over 2 to pi over 2 is that cosine is positive there. And in order to say the square root of cos squared is cos, I need cosine to be positive. So this is a case where using the symmetry is almost necessary. There are other ways to go about this, but in order to simplify the top the way we want, to say the square root of 4 cos squared theta is 2 cos theta, I need to know that cosine is positive. Right, it's the square root of x squared is not x, it's the absolute value of x. The square root of cos squared theta is not cos theta, it's the absolute value of cos theta. And as long as cosine is positive, those are the same thing. So that's why we use the bounds negative pi over 2 to pi over 2 here. If you were to go from 0 to 2 pi, then for a good chunk of that, cosine is negative from pi over 2 all the way to 3 pi over 2. Yeah, we can go back here for a minute. Push this up a bit. And I'll add the note here that from negative pi over 2 to positive pi to cos theta is greater than 0. So the square root of cos squared theta, which technically is the absolute value of cos theta, is equal to cos theta itself. If we were not somewhere cosine is positive, if the theta values we're working with included theta values that made cosine negative, then we would have to handle this absolute value very carefully. I made some comments about this when we learned trig sub, but then I told you all the integrals you're going to see in this class won't require you to think about that. Small fib. Here is one that requires you to think about it. I'll tell you, I'm not going to do this to you on a test. This was not something that will happen on an exam, but it's something you should be aware of. All right, let's finish this bitch up. We're almost done. It's been a little rowdy. Are you ready to continue? Maybe take a screen cap if you need it. I'm going to continue. Here we go. So that numerator is now 2 cos theta, and the denominator now is 2 minus 2 sine theta under a radical d theta. How do I do this integral? This is no longer hard. Good. What do I sub for? Very good. So I'm going to sub for the inside of the radical downstairs, which is 2 minus 2 sine theta, which means dz, if I differentiate this, is negative 2 cos theta d theta. What else do I need to do? I need to change the bounds. So before I jump in and try to calculate my antiderivative, because this is a definite integral, we're going to change the bounds. So when theta is negative pi over 2, z is going to be 2 minus 2 times the sine of negative pi over 2. So the sine of negative pi over 2 is negative 1. So this is 2 minus 2 times negative 1. That's 2 plus 2, which is 4. And when theta is positive pi over 2, z is going to be 2 minus 2 times the sine of pi over 2. The sine of pi over 2 is 1, so this is 2 minus 2, which is 0. I've got a 2 cos theta d theta, 2 cos theta d theta, that's negative dz, so I'll pop the negative out. This 2 is still chilling. My integral is now from 4 to 0. This 2 cos theta d theta is soaked up by the differential. The negative comes out. All that's left is 1 over the square root of z dz. We can flip the bounds over to suck that negative back in. Like this. And then 1 over root z is z to the negative 1/2. dz is still dz. Now my antiderivative. We add 1 to the power negative 1/2. We get positive 1/2. So this is going to be z to the positive 1/2. And we divide by that new power. Dividing by 1/2 is the same as multiplying by 2. That's from 0 to 4. I can pop this 2 out, making this 2 a 4. And then inside z to the 1/2 is the square root of z. So this is going to be the square root of z evaluated from 0 to 4. Which is 4 times the square root of 4 minus the square root of 0, which is 4 times 2, or 8. So this is a tricky one. Right? This is an integral that requires some delicate handling. The moral of the story is that arc length integrals, they were hard before in Cartesian coordinates. They're still hard now. Arc length integrals tend to be gnarly because of the square root. I got you. I want to do one more to show you that not all arc length integrals are terrible. If you need a screen cap, grab it. I'm going to move to one more example for the last 7 minutes. Here we go. Let's find the length of the polar curve r equals, how about 4 cos theta? There it is. Where 0 is less than or equal to theta is less than or equal to, just 2 pi, let's do 2 pi. So same sort of deal. Remember that the arc length for a polar curve, integral alpha to beta, square root of dr d theta squared plus r of theta squared d theta be the integral from 0 to 2 pi square root of dr d theta. So if I differentiate this, I'll get -4 sine theta. So this is going to be -4 sine theta all squared plus r of theta, which is just 4 cos theta. So 4 cos theta all squared d theta. And that's the integral from 0 to 2 pi of -4 sine theta all squared is 16 sine squared theta. +4 cos theta all squared is 16 cos squared theta. Theta. And now something nice happens. You can factor out a 16. Within that radical, and you have sine squared theta plus cos squared theta. And the sine squared plus cos squared is 1. That's integral 0 to 2 pi of the square root of 16 d theta. And the square root of 16 is just 4. So that's 4 integral 0 to 2 pi of d theta, which is 4 theta, evaluated from 0 to 2 pi. And that's just 4 times 2 pi minus 0, which is 8 pi. So this is not a bad problem, right? This arc length integral was incredibly nice. What kind of curve is this? Notice I didn't graph the curve to begin with. I want to sketch in polar coordinates r equals 4 cos theta. What is that? It is a circle, yeah. It's a circle centered. If you go through the exercise that we discussed the other day, you will find that this is a circle of radius 2 centered at centered along the horizontal axis. I'm going to go with my sketch here. So you could have found this arc length another way. Think back to that one arc length and distance problem you had in the previous homework set, where x was sine squared and y was also like cos squared. It turned out to be a straight line, and the particle was bouncing back and forth along that line. You didn't need to do an integral there. You could just draw the graph and go, oh, it's a little line segment. I'm going to find the length of that line segment by treating it as a triangle. Could have done the same sort of thing here. Could have found the arc length of this curve by recognizing it as a circle, and then just using the geometry formulas. We know that the circumference of a circle is 2 pi times the radius. The radius here is 2. So if you multiply 2 pi times that radius, you would get 4 pi. And this curve goes around the circle twice as theta goes from 0 to 2 pi. So sketching the curve is a good idea. Right? Sketching the curve is always a good idea. We could, although the integral here was not bad, we could have done this even faster if we drew the graph first. And you saw in the previous problems, we really needed to draw the graph because those informed the symmetry arguments that we made. And in one of those cases, the symmetry argument was necessary. All right, we are right at 12:35 now. And I want to say a few things in closing, and I'll let you guys go. First, thank you so much. Thank you for working hard and for caring about mathematics. I think the more time you spend doing this stuff, it becomes addictive, and you'll see its beauty the more love you put into it, and it will give you love back. Mathematics has this great way of healing the soul. So please continue to work hard on that. As you prepare for the final exam and you prepare for exam 3, be mindful of power series. Power series tend to be the thing in this class that give people the most trouble. So put plenty of time into the chapter 10 stuff, of course. Be proficient with this. Remember, exam 3 is not going to have any areas or arc lengths for polar curves. There will be areas and arc lengths for parametric equations, but the polar stuff, all the stuff we've been doing this week, not on exam 3. That stuff will be on the final only. So in preparation for exam 3, focus primarily on the power series. Make sure those skills are where they need to be, and the parametric stuff as well, although I think most people find the parametric stuff pretty straightforward. I do not have a practice test for the final, but I did post to Canvas a few reviews. So I've over the years made a handful of reviews when I was teaching at UF, and those reviews are up in Canvas under the announcements. And the last thing, if you, I have a PDF of this textbook. The textbook has a lot of really good studying tools. I'm going to be signing into my personal Google Drive here, so give me just 1 second. The chapter reviews in the textbook are excellent. So here. So I want to strongly encourage If you get through the study guide problems and you get through the other like prescribed stuff to work on problems, you can get the PDF that you've seen me using in class here. You've all paid for WebAssign, and that includes a copy of the electronic copy of the book. So I don't feel bad doing this, but if anybody asks you, you didn't get the PDF from me. You found it somewhere on the internet. Focus on power series, studying for exam 3. Make sure you're comfortable finding intervals of convergence, finding power series using the geometric series trick, differentiating, integrating power series, all of that. And then for the final, prep extra hard on the polar stuff, because the polar stuff isn't on any of the midterms, especially this calculus with polar stuff. It will show up quite a bit on the final. If you want to help with anything, come see me in office hours. Otherwise, I will see you guys on Friday for the test. Thank you again for the hard work you've put in. Good luck moving forward.